Hello everybody, Mr. Barry here, coming with you now the second unit. So we're going to move on from piecewise functions and absolute value functions to talking about quadratic functions. And we're going to spend a lot of time here. Technically, I think we're going to spend 2 units on different things that happen within quadratic functions. But this first video here is just to kind of show you again the parent function. A lot of you recognize this when we talked about this at the very first class. With quadratic functions. So I want to make sure that we understand what's going on with that. So when we talk about quadratic functions, we're talking about everything being based off of the parent function. And that parent function is going to be either f of x or y, and it's equal to x squared. So there's an understanding here with quadratics, and the word quadratic means that the highest exponent that we're going to see within the function is that little 2 right there. It kind of acts a little bit like an absolute value function, and what I mean by that is we'll see here in the picture. So I'm going to make a relatively small table of values over here. And one thing I want to point out here is that our vertex is at 0, 0. So much like the absolute value function we had, our vertex was at 0, 0 for the parent function. All right. And from there, we should notice that just like we had before, at the vertex, there is an imaginary line that we consider the axis of symmetry, and here our axis of symmetry would be at x is equal to 0. And that axis of symmetry will hold true for all the samples we're going to do. As we move on here in this problem, it's x is equal to 0. And it's a mirror on either side of the axis of symmetry. So let me just graph some other points here. So 1 and negative 1, they're the same exact distance away from the x value for the vertex. We do 1 squared, and that's 1. We do negative 1 squared, and that is positive 1 as well. So we have 2 points right here. 1, 1, and negative 1, negative 1. And to keep on going and following that pattern, we won't be able to tell as much of a pattern over here with the y values. All right, so when it came to absolute value functions, we had straight lines. We could use the slope. We used our a value to help us out with the slope. That's not the case here because of the squared. All right, so we won't be able to kind of tell the pattern from the y's. We'll still be able to use the idea of a mirror, but we won't be able to use that pattern. So 2 squared would be 4. Negative 2 squared, negative 2 times negative 2 would be 4 also. I'll graph those 2 points. There's 2, 4. There's negative 2, 4 as well. So again, we can see how that axis of symmetry kind of acts as a mirror here. Do one more. One more probably fits on the chart here. So I'll go down here to 3 and negative 3. 3 squared is 9. Negative 3 times negative 3, or negative 3 squared, would be 9 as well. So we do see that mirror action going on here. There's 4, so 5, 6, 7, 8, 9, and it would be on the same exact spot there. This is not a v. Absolute value functions were v's. We know that this picture right here for a quadratic, any quadratic, is going to kind of look like a U shape. So I'll try my best here to connect the dots. It's not a straight line. We have that U shape here for quadratics, and we say that that U shape, the technical math term for that is a parabola. And we've talked about a couple other things. We already mentioned the axis of symmetry. We're going to have a vertex here. All right, that vertex is going to be a maximum or minimum depending upon the problem. Here, since it's on the bottom, it's going to be a minimum. So we'll continue working on this. This is just kind of a basic thing to take a look here at our parent function, f of x or y, doesn't matter which one we use, could be equal to x squared, and how that mirror works and how we still have similar numbers over here when we use that mirror.